3, start. Hello everyone. Our project is about the Bosch production line efficiency production prediction, and our team members are Ayush Raj, Aditya Patil, Sudeep Paul, Aditya Singh, Shivam Pariyar, and Sandeep Mishra. Our group number is 6. Now, for this project, we collected our data from the following Kaggle competition link. Our broad aim is to predict internal failures of components using thousands of measurements and tests made for each component along the assembly line. Our data comprises a large number of anonymized features with information about the prediction line, station, and feature number. These features are broadly divided into 3 categories: numerical, categorical, and date-based features. Each feature represents the measurement of a certain parameter of a part as it is moved along the production line. Our target is to predict the parts which are identified by their unique IDs that will fail the quality control. Now, our data consists of measurements of 4 production lines and 50 stations. The measurements follow a particular part as it goes through different production lines, and they are a mixture of numerical, categorical, and date-based measurements. We have 6 files, namely test-categorical.csv, train-categorical.csv, test-date.csv, train-date.csv, test-numeric.csv, and train-numeric.csv. We can see the number of rows and columns in each file in the PPT as follows. Now, coming to the data visualization segment, we have plotted 3 scatter plots where we have mapped the number of missing values in a feature to the number of features having that particular number of missing values. The count of features has been plotted on the y-axis and the number of missing values is plotted on the x-axis. The 3 plots are in the context of numerical features, categorical features, and date features respectively. In the first plot, we can see that most of the numerical features have very large numbers of missing values. Similarly, in the second plot, we can see that only 2 of the categorical features have less than 9 lakh missing values. However, in the third plot, that is the date features plot, we can see that the number of features having a large number of missing values is relatively much less than the numerical and categorical features. Hence, we can say by looking at these 3 plots that most of the features have a lot of missing values, especially the categorical and numerical features, which make them comparatively less significant in our analysis than the date features.
In our pursuit of getting more insights about the date feature for better evaluation of our strategy for modeling, we have plotted 2 different curves in this graph. We are going to test it on the date feature for our test dataset and match it with the response we get from the train dataset. The red plot signifies the test data and the blue plot signifies the train data. From this graph, we can see that the 2 plots are highly overlapping. This implies that the train and test dates are almost the same. This clearly shows that the date feature renders our model better predictably. Now we can come over to the analysis of our numerical features. We use the parameter failure rate to calculate the chances of a part failing the quality control test at a particular station. The failure rate of a station is equal to the number of failure over the number of success for a particular station. The higher is the failure rate, the higher is the probability of failure of that part. As you can see clearly from the plotted graph, few stations have distinctively higher failure rates, namely station number 32, 38, station number 6, 24, 26, and 49 following them. From all of these visualization, we can conclude that our data is highly imbalanced, which will make our model highly biased. And classical algorithms of classification will perform poorly on this imbalanced dataset. Hence, our first priority should be to make our dataset balanced, which will be taken care of by oversampling the data.
Now, from the dataset, we observe that the data is very huge and the number of columns per file is very large, 1000 to 2000 per file, and each column represents a feature that corresponds to some measurement on a station or a machine. After removing all the missing values from the database and analyzing the data for initial part, we found that there were some values which are similar for some features in a particular row. After analyzing the data for every station ID pair for the first 10 rows, we observed that the feature value remained same for a particular station ID pair, and there is no effect of date on feature value. This gave us an idea that, to reduce columns by reading only one time for each station and minimize our dataset. Then we tested the whole database and observed that the probability of value being same across all features for the same station is 98.21%.
Yes. So considering we have thousands of features, we need to find a way to aggregate valuable information hidden below these features. As we saw from data feature engineering that for the same station, all feature columns are the same. From there, we got an idea that we can compress the feature columns for each station. But in the case of numerical data set, for each station, feature columns are not unique. Also, the failure rates at each station are different. So for capturing relevant information, we take minimum and maximum value across all features for each station. After this manipulation, for each station, we are left with only two columns, maximum and minimum feature columns respectively. Since in total there are 50 stations, now we have only 101 columns left for all stations combined. Moreover, in the feature columns, we have replaced all the null values with -1.
Categorical feature engineering. Through previous exploration, we noticed that categorical features are the most missing one among our three type of features. Besides, many features only have one unique value in whole column, which do not provide much help to our model. Therefore, we decide to pick features with most variety. We choose columns which have more than three distinct values. For feature selection, the string was converted into float type indicator variables.
Now, in the statistics part, we calculated mean, standard deviation, minimum value, maximum value, and more. Some of the calculated values displayed for station number 0 and line 0. From the data analysis, we also observed that station 24 and 25 has more than 200, which is maximum number of features, and at the same time, most of the stations has less than 20 features. But the worth noticing fact is that station 32 has only one feature.
We can move to the hypothesis testing part. So as we saw in the date feature engineering part, that we exploited the property of the data that in the date features for a single station across all features, in most of the cases the value were same. Almost in 98.2% of the cases the values were same. And we used this insight we got from data for date feature engineering. So the hypothesis we are framing here is also based on that observation. And the hypothesis, null hypothesis we have is going to help us in framing the strategy for date feature engineering. So our null hypothesis is that for all the columns in a single station I and j, the mean of I is equal to mean of j for all for any I comma j. And the alternate hypothesis is that the means are unequal. Then, as you can see in the table below, for when we plotted for 10 rows, most of the cases the for the same station the value is same. Now we can move to the testing part. How did we test our hypothesis? So as we had different multiple means, so the hypothesis testing method we used was ANOVA testing. We took station 0, and in station 0 there were 11 date features. We took only 1000 rows as the date number of rows was very large for calculation. We took 1000 rows and 11 columns and carried out ANOVA testing. For ANOVA testing, first of all, the significance level, the alpha we took was 0.01. As we have 1000 rows and 11 columns, so degree of freedom 1 will be 11 minus 1, that is equal to 10, and second degree of freedom is 999. The F statistic we got after applying ANOVA testing for only 1000 rows of station 0 was around 10 raised to the power minus 32. As we can see, 2.19 into 10 raised to the power minus 32. And the F critical value for alpha is equal to 0.01, which we got from the lookup table of F values, was 2.32. As we can see that F statistic is far less than F critical, hence our null hypothesis H naught cannot be rejected.
So finally, conclusion about data. First of all, data was very large. There were almost millions of rows, but large part of it was composed of missing values. Number of columns was also large for any model to run efficiently.
Redundant columns have been removed using different strategies in different types of data. Data is highly imbalanced, which needs special care in modeling part. Challenging part is dealing with such large data and filtering the number of features and using sampling methods while modeling with such imbalance.
Now, we have gathered some insights into our dataset. We saw that all the features are not important as they have a lot of missing values. We'll remove the missing values and refine the dataset as we have seen in our feature engineering section. After filtering from the large dataset, we are using 100 columns from the numerical data, 52 from date features, and 9 categorical features. Additionally, we saw that the data is highly imbalanced, and this problem needs to be tackled while we choose an applier model. The first step that we take in this pursuit is to choose a relevant evaluation metric. Hence, we have chosen the F1 score as our evaluation metric. We have justified our choice in the upcoming slides. Additionally, we also use the string indexer function for mapping categorical columns to numerical labels. Now, we have decided to use the cost-sensitive logistic regression model for this classification task. The reason we chose this model are as follows. It is a simple model, so it will prevent the chance of overfitting, which has been a major problem in a lot of classification problems. Now, as data is imbalanced, we weigh the positive, that is the failure part of the cross entropy loss at 150 and negative part as 1. The code snippet can be seen in the slide.
Now we will talk about the modified version of the loss function we used in our weighted logistic regression model. On the screen you can see a modified version of the cross entropy loss function. In logistic regression we use cross entropy loss function. But the loss function we used has weights associated with both the terms, and the weights are comparatively one is larger and one is smaller. The reason why we used this loss function was to tackle with the imbalanced dataset, as we failed to use any type of sampling methods in the data data engineering section. Here, the part of the loss function penalizing for wrong prediction when the output has to be failure is weighted more than the other part, because the number of failures are less, and in this way when a failure is not detected, this loss function penalizes the model more than the case when a success is detected as failure. We chose the weights by taking the ratio of number of failures to number of success. In the inverse ratio, we chose the weights for the two terms. Now we will move to the details of the training data and testing data we used. The training data we used had number of records at 47,155, and the testing data has 13,200 number of records. We chose this chunk of data from the whole bunch of data by random selection because we did not have the sufficient amount of resources for training a model on the larger data set. Also, we use no deep learning methods, and for a machine learning model, this amount of data set is sufficient for gaining the highest possible evaluation metric. Now we'll talk about the evaluation metrics we used. As our dataset was imbalanced, the classification evaluation metric was not going to be accuracy, because accuracy is not a good classification metric for imbalanced dataset. Hence, we chose to use F1 score and Matthews correlation coefficient, because F1 score combines the metric precision and recall into a single metric, and it is better than accuracy in the case of imbalanced dataset. Also, the Matthews correlation coefficient takes into account all the four elements of the confusion matrix, that is true, positive, true, negative, all four. Now we will move to the results we got out of our model. The F1 score came out to be 0.31%, which was comparable to the baselines of the problem on this existing dataset from Kaggle, which was 0.3 to 0.4%. And Matthews correlation coefficient came out to be 0.022, which was also relatively compared to the results of other existing baselines on this dataset, which were of the value around 0.027. Hence, the F1 score and Matthews correlation coefficient were suitable classification metric for this data set, and the reference we chose was the existing baseline models, and we were successful in competing with them. And you can see the code snippet. This was end of our presentation of this data science project.